ever stand near a railroad track as a train, like, thunders by, and wonder, how do those rails not just buckle under that kind of pressure?
Right.
Well, get ready to dive deep into the world of railway mechanics.
Okay.
Because today, we're
Yeah.
pulling back the curtain on the unseen forces that keep those trains rolling smoothly.
It's easy to think of train tracks as, like, simple static things.
Right.
But they're anything but.
Of course not.
Yeah, we're talking about a complex system designed to handle immense weight.
Yeah.
Vibrations.
Right.
Even noise.
Wow.
All while ensuring a safe and comfortable ride.
And we're digging into this with excerpts from Mechanical Behavior of the Track,
Okay.
a technical document that
Yeah.
frankly is not for the faint of heart.
It's pretty dense.
But don't worry.
Yeah.
We're here to decode the jargon and unearth the fascinating science beneath the surface.
Absolutely.
Think of us as your trusty translators on this journey into the hidden world of railway engineering.
I like that.
Yeah.
Our mission,
Okay.
should we choose to accept it,
Right?
is to understand how engineers predict and manage the stress strain,
Uh-huh.
and even the noise generated by trains.
Because it's not just about laying down some steel and calling it a day.
Absolutely not.
Right.
The key takeaway here
Yeah.
is that a train track is a system, a finely tuned orchestra of materials working in concert.
I like that.
You have the rails themselves,
Obviously.
obviously, but also the sleepers.
Okay.
Those are the cross beams, the ballast, the crushed rock surrounding the tracks, and even the ground beneath it all,
Right.
what we call the subgrade.
Okay.
Each layer plays a critical role,
Right.
and they all interact in ways you might not expect.
Okay, let's unpack that interaction.
Sure.
You mentioned something about elasticity.
Exactly.
Okay.
The entire track structure has a surprising amount of give to it.
Really?
Imagine for a moment those massive locomotives rolling over the rails.
Okay.
The track actually flexes and deforms under that weight,
Wow.
but it's designed to spring back into shape.
So it's not about being completely rigid,
Right.
but rather about controlled flexibility.
Precisely.
Interesting.
And that flexibility, that elasticity, is influenced by a myriad of factors.
Okay.
The type of soil, for instance.
Okay.
A rocky subgrade will behave very differently than one made of clay.
That makes sense.
Even those humble rubber pads between the rails and sleepers, they play a crucial role in absorbing vibrations and distributing load.
Really?
Oh, yeah.
It's like baking a cake, right?
Well,
You tweak one ingredient,
Right.
the whole texture changes.
Right.
You swap out sand for clay,
Yeah.
suddenly your whole railroad's got a different bounce to it.
That's a great analogy.
Is that kind of how they think about it?
Oh, yeah.
Wow.
And just like bakers have their recipes,
Mm.
engineers have something called track coefficients.
Track coefficients.
Yeah, these are numerical values that essentially quantify the give or resistance of each layer in the track structure.
So a high coefficient means stiffer,
Right.
less likely to budge,
Exactly.
while a low one means more flexible, more prone to bending under pressure.
You've got it.
Okay.
And engineers use these coefficients to design tracks tailored to the specific conditions of a location.
So they actually like factor that in?
Oh, yeah.
Wow.
They plug these values into models,
So they're like,
almost like virtual simulations,
right.
to predict how the track will behave under the weight of a train
Wow.
at different speeds
Right.
and under various environmental conditions.
So they're basically predicting the future of the track,
That's a good way to put it.
like some kind of railway fortune tellers.
In a way, yes.
Wow.
One of the classic approaches they use is called Zimmerman's method.
Zimmerman's method.
It's a simplified model,
Okay.
treating the track as a unidirectional system.
Unidirectional meaning what exactly?
It means we're focusing on the vertical forces at play,
Okay.
how the load of the train pushes down on the track.
Right.
Think of it as a starting point.
Okay.
It's a rough sketch before you get into the really fine details.
Gotcha.
Yeah.
But the real world is rarely that simple, is it?
You're telling me.
I'm guessing this is where things get even more complex.
You are right.
Okay.
Zimmerman's method is helpful,
Yeah.
but for a truly accurate picture,
Right.
engineers turn to more sophisticated tools, like the finite element method,
Okay.
or FEA.
Okay, hit me with it. What makes FEA the next level up?
Imagine taking that track and dividing it into a mesh of tiny,
Okay.
interconnected elements.
Okay.
Each element represents a small section of the track
Right.
with its own unique properties. The steel of the rail,
Okay.
the rubber of the pad, the
Right.
gravel of the ballast, and so on.
So instead of looking at the track as one big homogeneous thing,
Right.
they're analyzing every little piece of the puzzle
Exactly.
to see how they interact under stress.
Precisely.
Wow, that's cool.
This lets engineers model real-world conditions with incredible detail.
Really?
For instance,
Yeah.
they can analyze how the steel of the rail might deform under the weight of a train,
Right.
or how the ballast compresses and redistributes that force.
So we're not just talking about whether the track will hold up,
Right.
but how it might actually change shape over time.
Exactly.
Like it's almost alive, it's responding.
In a way, yeah.
That's wild.
We call this elastoplastic behavior.
Elastoblast.
Some materials, like the rubber pads, are elastic, meaning they deform under stress, but bounce back to their original shape.
Right.
Others, like certain types of soil, can undergo plastic deformation,
Okay.
meaning they change shape permanently under stress.
So FEA helps engineers predict not just whether a track will fail,
Right.
but how it might wear down over time,
Exactly.
allowing them to design for longevity and safety from the get-go. That's incredibly powerful.
Absolutely.
Wow.
FEA allows for virtual testing of different designs and scenarios.
So they don't even have to, like, build it to test it?
Right.
That's amazing.
Want to see how a track handles a heavier train?
Right.
Change the load in the model.
Okay.
Worried about extreme temperatures?
Right.
Adjust the environmental factors.
That's wild.
It's like having a virtual railway lab at your fingertips.
That's incredible. Talk about predicting the future. But I have to ask,
Yeah.
is FEA the be-all and end-all of track modeling?
That's a good question.
Or are there even more advanced techniques on the horizon?
Right.
Our source mentions something called unilateral contact theories.
Yeah.
What's that all about?
Now those
Yeah.
are fascinating.
Okay.
Unilateral contact theories try to model the often imperfect contact points between the rail
Yep.
and sleeper,
Right.
sleeper and ballast,
Okay.
and so on.
Right.
Instead of assuming perfect smooth contact,
Right.
which we know isn't always the case in reality,
Of course.
these theories factor in things like friction,
Uh-huh.
uneven surfaces,
Right.
and how force is distributed across those tiny points of contact.
So instead of assuming every contact point is a perfectly smooth handshake,
Okay.
we're getting into the messy reality of
Yeah.
like a fist bump with a cactus.
That's a colorful analogy,
Yeah.
but I think you got the right idea.
Okay.
It's about embracing the complexity of the real world.
Which, knowing reality,
Right.
is probably even messier than a cactus fist bump.
Yeah, it can be.
This is all incredibly impressive.
Yeah.
But where does it leave us in terms of understanding the big picture of railway mechanics?
Well, for one thing,
Yeah.
these principles help engineers design tracks that can handle the ever-increasing demands of modern rail transport,
Okay.
from high-speed trains to heavier freight loads.
That makes sense.
Right.
But it's not just about making trains faster and bigger, is it?
You're right. There's more to it than just brute strength and speed.
There's got to be more to it.
And that's what we'll delve into next.
Okay.
Remember those vibrations we talked about?
Right.
They're not just a structural concern. They also generate noise.
Right. Of course.
And engineers use those same principles of track mechanics to mitigate noise pollution.
Oh, okay. So we're moving beyond just keeping the trains on the tracks.
Oh, yeah.
We're talking about keeping the peace with the neighbors, too.
Exactly.
Tell me more about that.
You know,
Yeah.
it's funny you should mention keeping the peace.
Right.
Noise pollution from trains is a real concern,
Yeah.
especially in densely populated areas.
I can imagine living next to a freight line probably wouldn't be a selling point
Right.
for a quiet suburban home.
Not at all.
But how do you even begin to tackle noise in a system
Yeah.
as inherently noisy as a railroad?
It starts with understanding the source of that noise.
Okay.
It's not just the engine rumbling, as
Yeah.
you might think.
Right.
The vibration of the rails themselves,
Okay.
the interaction between the wheels and the track,
Right.
even the type of ballast used.
Uh-huh.
All these factors contribute to the overall noise level.
So it's like a chain reaction of vibrations,
Right now.
each component adding its own layer of sound to the mix.
Precisely.
Wow.
And this is where those track coefficients and modeling techniques we discussed earlier come back into play.
Okay.
By understanding how stress and strain travel through the system,
Okay.
engineers can pinpoint areas where vibrations are amplified
Right.
and design ways to dampen them.
So they're essentially trying to mute the vibrations at the source
Yes.
before they even have a chance to become noise pollution.
You got it.
That's interesting.
And they have a few tricks up their sleeves.
Okay. Like what?
They might choose a different type of ballast that absorbs more vibration,
Okay.
or modify the design of the rails
Uh-huh.
to minimize the surface area that's in contact with the wheels,
Right.
reducing friction and noise.
It's amazing how even seemingly small design choices
Right.
can make a big difference in terms of noise reduction.
Absolutely.
Wow.
And it's not just about tweaking the track itself.
Okay.
Engineers also consider things like train speed and maintenance.
Right.
A well-maintained train running on a well-designed track at a reasonable speed
Uh-huh.
is going to be significantly quieter than a neglected one barreling down the tracks at top speed.
That makes sense.
Yeah.
But let's say, despite their best efforts,
Right.
the noise levels are still a concern.
Right.
What then?
Well,
Are there any noise regulations in place?
you bet there are.
Really?
Most countries have established noise level standards for railways,
Okay.
especially in areas close to residential zones.
Hi.
These standards dictate the maximum permissible noise levels
Okay.
that trains can generate at certain distances from the tracks.
Okay, but how do you even measure train noise?
Well,
Do they have these giant decibel meters they stick on the tracks as the train goes by?
not quite.
Okay.
Though I'm sure that visual's pretty entertaining.
Yeah.
They use a unit called decibels,
Right.
or dBA,
Okay.
to quantify sound level.
Yeah.
But the measurement process is a bit more involved.
Okay.
There are different methods for measuring and simulating rail noise,
Okay.
often involving specialized microphones and software.
So it's a bit more sophisticated than just holding up a sound meter?
Definitely.
Okay.
And for good reason.
Right.
These measurements need to be accurate and reliable
Right.
to ensure compliance with noise regulations.
Right.
If a train exceeds the permitted noise limits,
Right.
railway operators could face fines
Wow.
or be required to implement additional noise mitigation measures.
So it's not just about being good neighbors. There are real consequences for exceeding those noise limits.
Precisely.
Wow.
And those consequences can be costly,
Yeah.
both financially and in terms of public perception. No one wants to be known as the noisy neighbor,
Right.
especially not when there are engineering solutions available to mitigate that noise.
Right, of course.
Yeah.
Speaking of noise mitigation,
Yeah.
I've seen those sound walls along highways.
Wow.
Do they use anything similar for railways?
You're exactly right.
Really?
Those sound barriers,
Okay.
or noise walls as they're often called,
Right.
are a common sight along railways,
Yeah.
especially in urban areas.
Yeah.
They work on the same principle as the ones you see along highways,
Right.
acting as a physical barrier to block or redirect sound waves away from sensitive areas.
It's fascinating how these principles we've been discussing,
Right.
the stress, strain, vibrations,
Uh-huh.
they all tie into this effort to minimize the impact of railways on the surrounding environment.
Absolutely.
Wow.
And it highlights how interconnected these seemingly disparate fields of engineering really are.
Right.
But before we get too far down the track on noise,
Okay.
there's another aspect we haven't touched upon yet.
Okay.
The impact of those vibrations on the track structure itself.
Right. We talked about how they cause noise pollution,
Right.
but what about wear and tear on the rails themselves?
That's a crucial point.
Okay.
Remember our chat about dynamic loads?
Yeah.
Those vibrations induced by the train's movement,
Right.
especially at high speeds,
Okay.
can significantly increase the stress on the track.
Really?
Think of it like this.
Okay.
Imagine jogging versus sprinting on a treadmill.
Right.
The impact on the belt is much greater when you're sprinting,
Right.
even though your weight hasn't changed.
Okay, I get it. Yeah.
So it's not just the weight of the train that matters,
Right.
but also the force exerted by its motion, its momentum.
Exactly.
Okay.
And just as a building needs to be designed to withstand those wind loads,
Right.
the track needs to be engineered to handle those dynamic forces from the train's motion.
Wow.
This is where the choice of materials,
Right.
the stiffness of the rails,
Yeah.
even the design of the sleepers,
Right.
all those factors we discussed earlier
Yeah.
come into play to ensure the track's longevity and safety.
So it's a constant balancing act.
Right.
You want a system that's strong enough to handle those dynamic loads,
Uh-huh.
flexible enough to absorb some of the vibrations,
Right.
and yet still cost-effective to build and maintain.
That's no easy feat.
You're telling me it's a testament to the ingenuity of railway engineers
Right.
who managed to strike that balance day in and day out.
Speaking of ingenuity,
Yeah.
let's circle back to those unilateral contact theories you mentioned earlier.
Okay.
Are those helping engineers tip that balance even further?
They have the potential to.
Okay.
Definitely.
Yeah.
While there haven't been any widespread numerical applications in railway engineering just yet,
Right.
the research is ongoing and showing promise.
So these theories, by factoring in the messiness of real-world contact points,
Right.
could lead to even more accurate predictions of how the track will behave under stress.
Exactly.
Wow.
And more accurate predictions translate into more refined design,
Right,
more efficient use of materials,
right.
and potentially even longer lifespans for our railway infrastructure.
Okay, that's seriously cool.
Yeah.
But before we get completely derailed,
Right.
pun intended,
Right.
we've covered a lot of ground here.
We have.
From the intricacies of track coefficients to the quest for quieter trains,
Right.
it's clear that railway mechanics is a surprisingly complex
Right.
and fascinating field.
It really is.
But I have to ask,
Yeah.
with all this talk of modeling,
All right.
simulations,
Yeah.
and advanced theories,
Right.
is there still room for good old-fashioned hands-on experience in railway engineering?
That's a great question.
Yeah.
And one that gets to the heart of how engineering evolves.
Okay.
While these advanced tools and theories are essential,
Right.
there's no replacing the intuition and practical know-how that comes from years of experience in the field.
So it's not a case of computers replacing humans.
But rather a partnership.
Exactly.
Okay.
The best engineers combine that deep theoretical understanding
Right.
with a keen eye for real-world application.
Right.
They can look at a track and intuitively sense potential issues
Right.
or come up with innovative solutions that a computer model might never have considered.
It's like the difference between reading about music theory and actually playing an instrument.
Right.
You need both to truly master the craft.
A perfect analogy.
Yeah.
It's that interplay between theory and practice,
Right.
between the virtual and the real,
Right.
that drives innovation and keeps the world of railway engineering moving forward.
You know, it's funny how we often take for granted these massive feats of engineering that allow us to, travel across countries at incredible speeds.
It is true.
Yeah. We hop on a train without a second thought about the intricate web of,
Right.
forces and materials and calculations that make that journey possible.
Right. It's like we're so focused on the destination that we forget to appreciate the incredible journey
Right.
happening beneath our feet.
And that's part of what makes these deep dives so fascinating,
Right.
wouldn't you say?
Absolutely.
Peeling back the layers of the everyday
Yeah.
to reveal the hidden complexities beneath.
It's like suddenly seeing the matrix code
Right.
behind the reality we take for granted.
Exactly. And in the case of railways, that code is constantly evolving
Right.
as we learn more about material science,
Right.
as our modeling techniques become more sophisticated,
Uh,
as we gather more data from real-world operations. All of that feeds back into the design and engineering of the railways of tomorrow.
So it's a continuous feedback loop,
Right.
always striving for greater efficiency,
Yeah.
safety, and yes, even passenger comfort.
Precisely.
Right.
Take, for instance, the development of high-speed rail.
Okay.
It's not just about laying down smoother tracks or building more powerful engines.
Right.
It requires a fundamental understanding of how those increased speeds affect every aspect of the system,
Right.
from the aerodynamics of the train itself
Right.
to the way the track interacts with the ground beneath.
It's incredible to think about all the factors engineers have to consider.
It is.
The weight of the train, the speed, the vibrations, the noise,
Yeah,
the environmental impact. It's a delicate balancing act.
it truly is. And it's a testament to human ingenuity that we've managed to achieve such high levels of,
Right.
performance and safety in a system as complex as a railway.
Absolutely. And it sounds like the journey is far from over,
Oh, absolutely.
with new technologies and approaches constantly emerging.
Remember those unilateral contact theories we talked about?
Yeah.
They're just one example of how engineers are pushing the boundaries of what we thought we knew about railway mechanics.
It's exciting to think about what the future holds for railways.
Right.
Will we one day have trains gliding silently on magnetic levitation tracks?
Maybe.
Or maybe even hyperloops whisking us across continents at supersonic speeds.
Who knows?
Right.
But one thing is for sure,
Yeah.
the principles we've discussed today,
Right.
the understanding of stress, strain, vibration,
Uh-huh.
and the interplay of materials, they will continue to underpin those future innovations.
It's like you said earlier, it's the code beneath the reality.
Exactly.
Yeah, and by understanding that code, we can begin to imagine and maybe even build entirely new realities.
Exactly. And that, I think, is a pretty profound thought to leave our listeners with.
Couldn't agree more. So the next time you see a train or hop on a subway, take a moment to appreciate the unseen forces at play, the tireless work of engineers past and present, and the incredible journey unfolding beneath your feet.
And maybe, just maybe, it'll spark a little curiosity, a desire to delve deeper into the hidden wonders of the world around us.
Because, as we've learned today, there's always more to discover, more to understand, more to marvel at if you know where to look. And with that, we'll bring this deep dive on railway mechanics to a close. Until next time, keep those minds curious, and remember, the journey of discovery never truly ends.